So welcome to Xendee's Microgrid 201 training, where we'll dive into multi-node modeling, one-line diagrams, and power flow analysis. I'm Lulu Arias, I'm the Director of Customer Success, and I'm excited to kick things off. This session builds on Microgrid 101 course, which you can access on demand if you haven't already. So let's get started. This is our agenda for today. I'll start by introducing multi-node modeling. Then we'll speak about when to use multi-node and also its components. Then I'll pass it to Giovanni, who will cover power flow analysis as well as heat transformer analysis. After that, we'll take a short 10-minute break and we'll close with 1 hour of real modeling example in Xendee, and Rita will be guiding us through that part. But before we dive in, let's introduce ourselves. I'm Lulu Arias, as I mentioned, the Director of Customer Success at Xendee. I have a master's in industrial engineering and an MBA from Columbia Business School. Before joining Xendee, I used to work at the Boston Consulting Group, leading teams on various different projects, but mainly focused in mining and oil and gas. And after the MBA, I decided to transition into green energy, and that's when I joined Xendee almost 3 years ago. Ever since then, I've been working closely with customers, helping them model their microgrid and EV infrastructure. Giovanni, Rita, I'll let you introduce yourselves.
Hi, everyone. My name is Giovanni Maronati. I'm a senior microgrid engineer at Xendee, and I focus on optimizing microgrids and distributed energy resources. My background is in engineering and economics. I hold a PhD in nuclear engineering from Georgia Tech. And before joining Xendee, I worked at Westmore Partners and Argonne National Laboratory. Leave it to Rita.
Hi, everyone. My name is Rita. I'm a customer success engineer with Xendee. I have a master in engineering from UC Berkeley, and my background is in environmental engineering. I used to work in surface water and hydrology, but now I have transitioned to clean energy. At Xendee, I'm responsible for supporting our customers and making sure they have the best experience. So if you ever send a support request to us, I'm probably the one taking the first look at it. Other than that, I also help make sure our customers have the best support they need as far as help, training, webinars, as well as consulting.
Thank you. So let's get started. What is multi-node modeling? It is basically a way to represent a complex energy system as a network of connecting points or nodes where energy is generated, consumed, or transformed. Think of a university campus with multiple buildings, each with unique energy needs. Multi-node modeling captures how power flows between these points. Unlike other simpler models, it factors in losses and voltage behavior for a more accurate design. So let's compare now single node and multi-node approaches. In a single node model, all loads and technologies are lumped into one point. It's great for small sites, but it ignores spatial details. For example, modeling an airport as one load misses how energy moves between terminals and hangars. Multi-node modeling, however, assigns each load and technology to its physical location. This lets you capture cable losses, optimize equipment placement, and design for real-world complexity. In Xendee, you can move from a single node to multi-node to one line with a couple of clicks. So let's start with single node approach. Imagine modeling, once again, an airport as one big point, lumping in all loads and technologies together. It's a great starting point for this quick techno-economic optimization, but it skips the details of how power actually moves. So next, we would enable the multi-node feature and break that site into individual nodes. Think terminals, hangars, control towers, each with its own loads and technologies. This lets us factor in spatial details, cable losses, voltage constraints, giving us more realistic power flow picture. Finally, we take it further in Xendee into the one-line tool. And this is where we dive into the detailed electrical simulation, analyzing power flow and short circuits across the multiple node system with high resolution data. So we'll see all of this once we dive into Xendee, but I wanted to give you this overview picture. Okay, so when should we use multi-node modeling? It is critical for large distributed sites like airports, naval bases, university campuses. For example, at an airport, you might place solar on a terminal for high visibility, then batteries near air traffic control for reliability, and a generator at a remote hangar. Multi-node modeling helps you right-size technologies and optimize as well the cable and transformer cost by accounting for distance and losses. So why go with multi-node? First, it offers enhanced system fidelity, detailed insights into each node's energy use and generation, and you can place technologies precisely on high-demand buildings. Secondly, it optimizes cost by balancing capital expenses like transformers with operational savings. And third, it includes basic power flow analysis, ensuring voltage stability and accounting for losses in cables and pipes. So let's now break down the key components. Nodes, as we mentioned before, are these connection points like substations where energy is generated or consumed. Loads represent demands, electrical, thermal, and each load in multi-node ties to a specific node for accurate modeling. Then we have transformers that step voltage up or down, connecting nodes with different voltage levels. We also have cables that carry power between nodes with losses based on length and material, and these components define how the system behaves. On the thermal side, we have heat and cooling pipes that transport hot or chilled water, critical for systems, for instance, with combined heat and power, and their losses depend on length and installation quality. Technologies like solar, batteries, generators are also assigned to specific nodes, allowing for more precise placement. Together, all of these components let you model both electrical and thermal energy flows for a more holistic design. That basically wraps up our introduction, and now Giovanni will dive into the technical details of power flow and heat transformer analysis. So over to you, Giovanni.
Thank you, Lulu. So now let's switch gears into the power flow analysis. So up to now, we've framed why multi-node modeling matters. Power flow is basically where we solve for voltages at each node. We solve for real and reactive power flows in each branch, and we calculate the losses across the network. Basically, it's a steady state snapshot of how electricity moves across the microgrid. So what is power flow analysis? So it's how we calculate, as I said, node voltages, branch flows, and system losses. And in Xendee, those results go into the optimization, which tells us where the technologies should sit and what sizes they should be. Most distribution systems that we model are radial, with nodes or buses connected by cables and transformers, and with loads and on-site generators that hang off those nodes. Here, just a couple of definitions to keep us aligned. Active power, it's what does the useful work, and reactive power is what supports the voltage and magnetizing needs in the network. Next slide, please. So in Xendee design, as I said, power flow is coupled to the techno-economic optimization. This is done via optimal power flow on an hourly time step. So Xendee design basically decides not just how big the DRs should be, but in which node to place them, which cables or transformers to use, and how to operate them on an hourly basis. Basically, the key constraints that we enforce, in addition to all the constraints about the microgrid, the branch capacity to make sure that we are not overloading cables and transformers, voltage limits, and we also enforce losses. Xendee one line, on the other hand, is a more detailed standalone analysis that is not part of the optimization that we're going to cover in a few slides. So to make the optimization fast and robust, we use LinDis flow. So it's a linearized distribution flow approximation of AC power flow. And we have the assumptions of a balanced three-phase system. This combination of assumptions helps us speed up the optimization while preserving the system, the essential system behavior. We also designate a slack bus, which is typically the utility connection, to anchor the system voltage and provide and absorb any power balance errors in reactive and active power. So basically, we enforce voltage bounds at each node. We apply active and reactive power branch capacity limits to prevent overloads and guide the cable and transformer selection. And we compute losses through branch resistances and impedances. So the optimization basically evaluates different sets of cables and transformers from a technical and economical standpoint and picks the cables and transformers with the correct length that satisfy all the constraints that provides the minimum cost for the microgrid to operate the microgrid. Now we're going to go through some screenshots of what these pages in Xendee look like, where we put in all the cable and transformer parameters. So this is the typical cable page. And these are all the parameters that we use in our model. So when you already know your cables, you can put in the parameters and lock them in. We also take user-specified cable parameters, so impedance, rating, and cost, and the optimizer will honor those limits and economics. And also you can turn on Xendee sizing, which is shown in the next slide. And basically, if you don't know the exact cables, you can let Xendee size these cables using a simple method. We also provide a catalog, so the optimizer picks a size that meets the capacity and all the constraints of your system. And we also have a more thorough method, which is that follows the next standard. So for stricter designer workflows, we can apply the National Electrical Code rules for ampacity and conditions. So the results align better with common electrical design practice. And then we have transformers. So it's similarly to cables. We put in all the parameters if we know them. So you can fix the transformer, make a model and rating, and the model will enforce all these limits and optimize around these parameters. But you can also turn on Xendee sizing similarly to cables. And then we co-optimize the transformer rating, losses, and cost alongside all the other DER decisions. Now we're going to go into what is one line. So the Xendee one line, basically it's a diagram that simplifies what the electrical system looks like. So it shows the power paths, the nodes, the cables, transformers, DRs, without really worrying about the physical layout. And this is perfect for validating the topology of the system. And Xendee one line in the next slide is basically our detailed power system analysis environment. Here you can either start from scratch, so build in your power line diagram from scratch, or also import it from design. So once you've built your project in Xendee design, you can export your system into one line. And this auto arranges the diagram. And even you can add a component, so it auto arranges as you add components. It can tie it into a GIS map. to pull the cable lengths automatically. And it also had an extensive cable catalog. So a common workflow is usually you optimize in design, import into one line, and do deeper electrical checks. So here, basically, you run snapshot power flow. So this is not tied to the optimization. It's just a detailed electrical evaluation. So you can change the delta Y configurations, choose any slack buses, and import dispatch from Xendee multinode. So you import a certain hourly dispatch, and then you run the analysis for that specific hour. So again, this is not tied to optimization, but it's a very detailed analysis for a specific timestamp. And the outputs include nodal voltages, line currents and flows, losses, and transformer loading. Also, one line flags the overloaded branches, so you can immediately see where you have any branches that are overloaded. Next slide. So here now we move a little bit, we shift our gears into heat transfer analysis. So multi-node is not just electrical. So we model also thermal and cooling needs for a microgrid. So many microgrids move thermal energy, so either hot or chilled water, for example, between buildings. And we model that using thermal pipes that connect different nodes. So each pipe has a heat transfer capacity and the loss coefficient that captures the insulation quality and length, similarly to cables in an electrical grid. So next slide. Sorry, 29, it was the correct one. So conceptually, the thermal model parallels the power flow, but it's deliberately simplified. So we're not doing advanced thermodynamics or heat transfer analysis. We just make sure that we are enforcing a thermal capacity limit on each pipe, and we calculate heat losses over the distance through a loss coefficient. That's enough for most applications to reflect the key economics. For example, if evaluating whether a CHP system or a central chiller can serve distant buildings with acceptable losses. So in practice, the optimizer trades off whether to use larger pipes that have better insulation that cost more, but would reduce the thermal losses, or use smaller or poorly insulated pipes that are cheaper but waste energy as energy is transferred between nodes. Again, here multi-node shines because it captures those site-wide interactions, and all of this is included in the optimization. And similarly to what we do with the cables, here we can define the parameters of the pipes. So we define a thermal capacity, which represents the maximum heat that can flow through the pipe, and the loss coefficient that defines how quickly heat degrades via the length. These are very clean inputs, very simple inputs, but these lead to very strong results. Yeah, so these are just a few slides on the power flow and heat transfer, and now we can move on to the demo.
Great. Thanks, Lulu. Thanks, Giovanni. Welcome back, everyone. So this portion is going to be a hands-on demo model where I'll go through a actual microgrid example in Xendee's design platform, focusing on a multi-node example, and it's up to you, but you can follow along and recreate the steps that I do so that you also get the experience and workflow of modeling in multi-node. So what I'm going to do is share my screen so that you can all follow along. So yesterday, you should have gotten an email notification saying that Rita Chen shared a Xendee project with you in design. So you can access that project directly by clicking on the link in the email, Or if you log into your Xendee trial account, you should see that you have project, my projects folder, and then you should see a subfolder that says shared by Rita Chen. If you don't see the project or you're having trouble locating that example project and you want to follow along, just put it in the chat that you need the project, and Lulu will send the project to you. So remember that this demo in this course has been focused on multi-node, which is a more advanced feature of Xendee modeling. And if you are new to Xendee modeling, want to learn more about the basics of Xendee, which we highly recommend that you do, be sure to check out either the Microgrid 101 recorded videos. Microgrid 101 focus solely on just the basics of microgrid modeling in Xendee. It focused purely on just single node modeling, which is a lot more straightforward than multi-node. Additionally, we have a series of on-demand resources for you to learn how to use Xendee. So in your account as well, you'll see this tab that says Help Center. And under the guided walkthrough page, we have a lot of basically self-guided tutorials that you can watch. So under the basic onboarding modules, you'll see what we call our 7 basic modules. And this is where we generally recommend our new users in Xendee to start, because these modules will guide you from the very beginning of setting up a project to setting up all of your necessary project settings, finances, load profiles, technologies, all the way to when you're running a optimization and interpreting your results. There's 7 basic modules, and they will also cover the biggest analysis configurations in Xendee. And hopefully by the end of these modules, you should feel a lot comfortable with at least starting a project in Xendee. We also have a section of what we call feature deep dives, and these are dedicated to more specific technologies or tools in Xendee. For example, you'll see they're dedicated to technologies like CHP, adding a BESS, wind turbine. So these kind of cover, more specific DERs. So highly recommend to check these out as well if you're interested in a specific DER. And lastly, we also have what we call our platform documentation, which is like a complete user manual of the software. You'll see we have lots of pages on our different analysis tools, technologies, and as well as settings in Xendee. So if you have a one-off question or you need information about how to set up something in Xendee, this is also a good place to start. Okay, so now let's dive into the hands-on modeling portion. Oh, sorry, wrong tab. Okay, I'll let everyone take a moment to pull up the project I have shared. It should look something like this. So just to give an overview on this project, as you can see, we have several buildings here, and this is actually a hospital complex. Remember, one of the best use cases for power flow is when you have a site like this that has, several different buildings, each with their own demands or DERs. And you can see that I have set up a lot of the model already. When you, just as a background, when you start a project in Xendee, you usually have to set up everything. And that includes your electricity tariffs, your fuel prices, your financing methods, any incentives, and of course, your loads and your DERs. In this case, I have set up all of this for the sake of keeping this presentation demo short, but just know that this is partially set up for the sake of this exercise. So you'll see that we have this hospital here. at the very top, you'll see that we have our controller symbol and our utility connection. So our utility connection represents our site's actual connection to our local utility. And you'll see that I have entered here the voltage as 69. And everything else I'm just going to leave as a default, but feel free to, explore each of the tabs. So that's our connection, and you'll see that we have our two buildings here, which I've just called node 2B node 2 and node 1. And on node 2 here, you'll see that we have this load, which again, I've entered all this information preemptively, but you can explore options for entering load shapes if you like. Here we have an electricity profile as well as a water heating profile. And you'll see that every load in multi-node will come with a power factor that you can change. In reality, a 100% power factor is probably not realistic, but for the sake of this exercise, I'm just going to leave it as a default. And at this node number 2 here, I also have an existing boiler that meets the water heating demand, as well as a solar PV. And here you'll see that I have left the solar PV as considered because I want Xendee to tell us how much, if any, solar PV is optimal for investment in this multi-node model. And then here we can move over to what I call our node 1, which is this building over here. Here you'll see that we have another load icon. So this represents the load for this specific building, which is going to be different from our other node. So here we also have an electricity profile. And then here I have put something different, which is going to be a cooling profile. And here to complement our cooling profile, I have an existing electric chiller. And here we also have an EV charging station. So if you click on the EV demand, you'll see that I've already set up an EV load shape, and this is separate from our building's electricity load shape. And I'm not going to go into too much detail about the EV demand, but we also do have a guided tutorial on EV modeling if you want to learn more about that. And unlike model 2 or node number 2, node 1 here, I've already created kind of like a precursor node here so that we can step down the voltage to node 1B, which is the actual building. We have to step down the voltage a few times, but we'll get to that. So back to our overall building model. So what we need to do is connect our utility connection to both of our nodes 1 and 2 so that they can both get power. Right now, the model is not complete. If you just run an optimization as is, it's not going to work because they're not connected. Okay, so let's start with adding some symbols to the model. So at the very bottom here, you're going to see the symbols tab that pops out, and you'll see we have some symbols first are related to multi-node modeling that we reviewed earlier, like our cables, transformers, thermal pipes, as well as extra symbols to represent a node, building loads. And then if you move on, you'll see we have our technologies that are in this model already. And we've already added all of those technologies to this model, so you don't have to do it, but these symbols are here in case you want to add more. And if you want to add additional technologies or enable additional technologies for your model, you can do that from our settings window. You'll see that I have only a select few of the technologies enabled just to keep my window clean. But if you do want to enable adding, say, like a fuel cell generator, you can do that if you want. This just allows you to be able to add a fuel cell generator to your symbols bar. Okay, so what we're going to do first is add a feeder node. So go to your symbols bar here and double click on the node icon. And this is going to bring up our node setup window. At the top here, you can change the name. I'm going to change this to name to feeder because it's going to basically be responsible for feeding or distributing power to the different nodes or buildings on our model. You can see that Xendee directly calculates or approximates its coordinates just based on the map and where you place it. If I move it, this coordinate will directly update. And voltage here, you'll see that it says 0 right now, and that's because it's not connected to anything. Once we connect it to the utility via the cable or transformer, this voltage will update. And here under costs, you can enter any financial costs or labor costs that you think will be associated with installing this node or connection. I'm just going to leave it as blank for now. And once you're ready, be sure to click the save button at the bottom left-hand corner. If you don't click save, it will not save your progress. So be sure to click on the save button. And once you do that, you'll see we have now our feeder node icon on the map. And you can move it around to wherever you want, but I'm just going to put it like directly here under the utility connection. Okay, and now we need to connect our feeder to our utility connection, and we're going to do that with a transformer. So again, at our symbols bar down here, I'm going to double click on the transformer. And you'll see that once you click on a transformer, it's going to ask you which two nodes you want to connect with this specific transformer. In this case, I'm going to select the primary node as our utility connection because that's where I want the electricity to be sourced from. And then I'm going to select the secondary node as our feeder node. And then click Add Transformer. So then this will bring us to our transformer setup page. At the top here, you can rename your transformer if you want. And you'll see that it shows our primary side connection, which is our utility, and our secondary, as well as our corresponding voltages. Remember, our utility connection's voltage is 69. But here, I'm going to then enter the voltage that we want to step down to at our feeder. In this case, I'm going to put in 14 kilovolts or whatever voltage your feeder or secondary connection would need. And then after that, we have a few options as far as your investment specifications, as well as your power specifications. So the most basic option is to enter the values yourself if you already have a transformer model or manufacturer that you want to use. Or you can leverage our catalog. So on the left-hand side here, you'll see we have this catalog option. And we have a whole list of cataloged transformer options. You'll see they're from different manufacturers or just have standard common ratings, impedances, or specifications. So this is one option. You can also utilize what we call our Xendee sizing option. Remember from our presentation earlier, Xendee sizing is a functionality that will automatically pick an appropriate transformer for you based on your site's voltage requirements and constraints. So if you enable this, Xendee will automatically pick a transformer from our built-in catalog that meets your project's requirements. For this specific transformer, I'm going to manually enter our inputs. And of course, you can enter any cost you want. This is just an example. For power flow, this is a pretty big transformer stepping down from the utility. So these are the values I'm putting in. And these values will impact the power flow calculations once we run an optimization. Okay, just to summarize what we did here for the transformers, you have a few options as far as inputting your specifications. You can do it manually like we just did here. You can use the catalog, which has a lot of common models or manufacturers. You can also save your own entered information to your own private catalog. So for example, if you're always using the same transformer for your project, you can save it to your catalog so that next time you model, you can just pull it up directly from your catalog instead of re-entering everything. And then of course, you can use a Xendee sizing option, which will let Xendee automatically select an appropriate transformer for you. And once you are done setting up everything, be sure to click Save in the bottom left corner. Okay, and now if you zoom into our utility connection in our feeder area, you'll see that we now have this symbol that connects between them. It's a little transformer. And if you want to make any changes to that transformer, you can double click on this symbol directly on the map, and that's going to pull up our transformer setup again. Okay, so now our feeder is connected to our utility. And then if you go back to our feeder window, you can double click on that feeder node. You'll see that its voltage has updated to what we specified the secondary side voltage to be via the transformer, which is 14 kilovolts. Okay, and now what we're going to do is connect our feeder node to our node 1 here. And we're going to do that with a cable. So in the symbols bar at the bottom, let's go ahead and double click on our cable symbol. And it's also going to ask which specific nodes you want to connect via this cable. So I'm going to select feeder as our first node, and then node 1A as our other node. Remember, node 1A is kind of like the first node at our building number 1, our primary node. And then you can click Add Cable, and this is going to, again, bring up our setup window for this specific cable. And you can enter a unique name. So for example, you can say feeder to node 1 cable. And for cables, you are going to see that Xendee is going to automatically calculate a line length or the distance of your cable based on the distance between those two nodes. And what's cool about this functionality is that if you adjust the cables on the actual GIS map, if you drag it around, Xendee will automatically update the calculations. But of course, if you already have like a cable length in mind, you can totally overwrite this and enter in a length. And you'll see that the voltage is going to be 14 kilovolts because that's the voltage at the feeder node. And as always, we have several options for inputting your investment as well as your power flow specifications. You can always do it manually. And then we also have a catalog for cables. So in this case, say I'm interested in a copper cable. I'm going to type in CU in the search bar here. And then I'm going to use this Prismian cable as an example. I'll let everyone take a moment to catch up. Okay, so I'm going to select this cable, and you'll see that it already has a lot of its power flow specifications in this catalog, but be sure to pick something with an appropriate, ampacity and rating for your cable. So I'm going to select this cable, 15 kilovolts, 100% copper. And that's going to pull in that cable specification to here. So you'll see it's already filled out all of this. And for cables as well, we also have the Xendee sizing option, which again is going to let Xendee select a cable for you from our catalog based on your site's power flow and constraints. And if you have the cost or estimate of a cost, you can put it in, but it is not required. But for this exercise, I am just going to input the cost. This is just an average cable cost. And then once you're done with that, click Save on the bottom left corner. And now you'll see that there's a direct cable between our feeder node and our node 1A. It's going to pick the closest distance, which is likely not going to be cable that way. So you can actually adjust the cable layout by clicking on this little connector dot in the middle, and that's going to allow you to kind of reorient and position the cable by adding in different segments. So you can totally move this around. You can add in extra segments that better estimates your cable's layout. And then now that we've done that, the cable length has changed. So if you go back and double click on this actual cable line, like the orange line, you'll see that our line length has automatically updated just based on Xendee's calculations. But you can always overwrite that if you want. Okay, so now we have connected our feeder to our node 1A, which means that our building 1 here can now receive electricity or send electricity. And now we need to do the same thing with our building 2/node 2 over here. And we need to provide the same power flow and step down as we did with node 1. So we need a primary node 2A first. So let's come over here, and in the symbols bar, double click on the node symbol again to add a primary node. At the top here, I'm going to name this to node 2A. And again, the voltage is 0 for now. That's because it's not connected to anything yet, but it will update once we connect it. And I'm going to leave the install cost as just blank for now and click Save in the bottom left-hand corner. And this is going to add a node 2A to our map. And I'm going to just reposition it over here. So now I need to connect node 2A to the feeder. So again, in our symbols bar down here, double click on the cable symbol. And for this one, we're going to connect it from the feeder to node 2A, which is our primary node at building 2. Add cable. I'm going to rename it to feeder to node 2A cable just to keep things organized. Again, it's automatically calculated line length just based on the distance between the two nodes, but feel free to adjust that if you want. And for this one, I'm just going to use the same copper cable that we had before. So I'm going to enter or search CU to get our copper cable. It's going to be the first one at the top. And that's going to bring in our power flow specifications. And it's also going to show on the left-hand side which cable you have selected. I am going to input that cable cost again. And then click Save once you're ready. So again, you'll see that this yellow-orange line has been directly added to our map. That just symbolizes our cable. And you can, drag it around, reposition it if you want. Okay, so now that our feeder is connected to our primary node at building 2, we then need to step down the voltage once more to our node 2B. So in the symbols bar at the bottom here, let's click on our 3-phase transformer. Our primary node is going to be our node 2A. And then our secondary is going to be our node 2B. Let's add transformer. Okay, so here I'm going to enter the secondary side voltage as 0.4, which is also just the same one as building or node 1B's secondary side voltage. And for this one, I'm actually going to select a transformer from our catalog. And for the sake of this exercise, I'm just going to pick the very first one to keep it easy. And of course, you can enter a install cost if you want. I'm just going to estimate 600K for this transformer. And once that looks good, feel free to click save. And now you'll see our node 2A is connected to node 2B via a step-down transformer. And this means that our node 2B's building load can get electricity from node 2A, which connects to the feeder, which connects to the utility. So our building load here can get electricity from the utility. And remember that these cables are bidirectional. So my node 2B here, it has a solar PV, and if it's economical or if we want, it can sell or send solar PV generation output to our other node via this long chain of cables, or it can sell solar back to the utility if that's an option. Okay, so I'm going to let everybody catch up. If you have any questions about what I did, or if you missed a step, feel free to put it in the chat, and Lulu or Giovanni can help with that. So just to summarize what we did, remember we have a hospital model with 2 different buildings here, building 1 and 2. And we had our utility connection at the top, but it wasn't actually connected to our different nodes here. And remember, you always have to provide some sort of connection or branches to send the electrical power to your different buildings. So in this case, we've added a feeder node, which just represents like a distribution node that's responsible for sending power to our different buildings. And then from our feeder node, we've added cables so that we can actually send electricity to our building 1 and 2. And we've stepped down the voltages along the way so that they're at a usable voltage for just like a regular small building. Okay, so now our model is complete. So we're ready to run an optimization to see what that looks like. So at the top here, you're going to see this main tab that pops out. And click on the optimize button. And this is going to bring us to our optimize setup window. If you're not familiar with Xendee yet, or you just got started with Xendee, an optimization is what we call one of our technical economic analysis that actually runs the simulation and finds the best dispatch as well as DER sizes for your model. So basically, every time you want an actual analysis, you need to run an optimization. So at the top here, always enter a descriptive name for your optimization, because once you run a bunch of optimizations, you're going to want to be able to keep track of which optimizations you ran and, what settings you had for each. In this case, we only have one optimization so far, so I'm just going to call this like a reduce cost optimization with consider solar PV, because remember we have, no leading spaces. Okay, because remember we have a solar PV icon to help us consider or find out what's the optimal size of solar PV for our site, if any. On the right here, sorry, you're going to see a few options as far as your optimization configurations. For now, I'm just going to leave these as a default. But feel free to check out our platform documentation if you have questions on any of these. And then if you scroll down to our optimization decision, this is where you pick the objective function for your optimization. Remember, Xendee is powered by a algorithm that relies on an objective. So in this case, I'm going to select reduce cost as my objective because I want Xendee to find the cheapest and most economically efficient solution for my site. If you are interested in reducing CO2 instead of reducing costs, you can change that to reduce CO2. But for this exercise, I'm just going to select reduce costs, and Xendee is going to find me the best solution and dispatch that minimizes my annual system costs. And let's scroll down to our reference model. So the reference model is going to be the model or scenario that our new investment scenario is going to be compared against. So what that means is that in our new optimizations report, we're going to see cost and emission savings, and that has to be calculated against a reference. So by default, your reference source is going to be what we call Xendee computed, and that's just going to be whatever your existing assets are. And remember, our existing assets in this case are just going to be our utility connection, as well as our existing DERs. But you can use one of the other reference sources. Say, for example, if you don't have a reference scenario, that's totally okay. Or you can enter in your own manual values that you want to compare against. And then to the bottom here, we're going to see options for analysis configurations. And you'll see that a couple of these configurations are actually going to be disabled for multi-node, like time series, multi-year. These are not supported for multi-node objects or multi-node projects. They're only going to be available in regular single node projects. Remember, we discussed earlier, single node projects is when you just have one node and one aggregated load. So no power flow, no cables, no transformers. And for us here, we're actually going to enable consider power flow. You can totally leave consider power flow as off, but this is not going to actually consider your cable's losses, voltages, or requirements. It's basically just going to treat your multi-node model as if it was kind of like a single node model where there's no power flow involved. But if you turn this on, which we are going to do for this exercise, you're going to see a few options regarding power flow. First, it's going to give you the option to enforce voltage limits. The default is going to be the standard values 0.95 to 1.05, which I'm going to use for this case. And you're also going to see a toggle for consider losses. If you leave this off, Xendee will not calculate your system losses from like your cables or transformers. If you turn this on, it will calculate those losses. And branch capacity is going to enforce the capacity limits of your cables and transformers. Again, if you leave this off, it's just going to assume infinite power capacity for your network. I'm going to enable both. And once you're ready, you can then click Run Optimization. Oh, hold on, I got an error. Okay, so it's because I have this extra node here. I'm just going to delete it. Yeah, so in your multi-node model, every single node that's present in your project has to be connected before you run an optimization. So if you just had like a rogue node like I did, you need to delete it first. Okay, then now we're actually ready to go back to run an optimization. Okay, so I have the same settings as before, consider power flow, and all of these enabled. So now we can actually run an optimization. And once you do that, you're going to see a few little pop-up messages from Xendee just letting you know that it's getting started on the analysis. And while this is running, you can actually keep making changes to your model. Because Xendee, you can actually run up to 3 optimizations at the same time. So while waiting for this optimization to run, you can, quickly go into one of your windows, change something, and then run another optimization. And Xendee is going to run up to 3 optimizations at the same time. So since this is a multi-node project, it's probably going to take a couple minutes for this project optimization to run. And because we have power flow enabled, that's probably just going to add a little bit to the extra runtime. Basically, anytime you have some sort of complex analysis configuration, that's going to take a little bit longer for the optimization. For a regular single node optimization, those only take like less than a minute. So while we are waiting for this optimization to run, I'm going to let everyone take a little bit of time to catch up. If you have any questions, feel free to put them in the chat.
I think Vita team has problems dragging and moving the transformer and cables to the correct location. So if you can kind of show how to do that once again, it will be helpful. Thank you.
Sure. So for any of our symbols in our platform, you can always drag it around on our GIS map here. So for example, if you have like the transformer here, you can drag it around by like moving these 2 nodes that it's connected to. Remember that our transformer, it's not tied to like an actual distance like the cable is. So it's just going to basically be in the middle of whatever your 2 connected nodes are. So if I move like my utility connection, it's going to move the transformer as well. But this distance, at least for the transformer, this is purely symbolic. As far as multi-node cables, you should just be able to move around by dragging the dots on your map directly. I hope that helps. Okay, so it looks like my optimization has finished. You'll get this pop-up at the right here that says your analysis has been completed. And you can access that report in several ways. You can directly click on this here, or you can first go to our results page. So the results page is basically where all of your analysis reports are going to live. So let me click out of this. So you can click on that pop-up that showed up when your analysis finished to get there, or at the top here from the main bar, you'll see we have a results button right next to our optimize button. So let's click on results here. And that's going to show our optimization we have just done. Of course, I only have one optimization here, but if you run a bunch of optimizations, they're all going to be in here. And this is the name, the title that we named our optimization. And this is going to summarize our analysis type here. So remember, reduce cost is what we picked our objective to be, because we wanted Xendee to find the most cost-efficient solution for us. And amortized cost just refers to the financing method that we picked. We didn't go over financing in detail in this course because it was covered in Microgrid 101, but you can learn more about financing in one of our guided tutorials. And we have this power flow button here because we have enabled power flow. So these are just labels to help you like quickly see what options you have enabled. So over here, let's click on view report. And that's going to bring us to our actual optimization report. So at the top here, you're going to see the summary table that summarizes your annual system costs and your annual carbon emissions. Remember that you're always going to have a reference scenario if you pick Xendee Computed as our reference model, or if you like enter in your own reference costs, this is what it's referring to. And from these references, we calculate a percentage of savings. So for both costs and emissions. In this case, it's saying that our new scenario, which is also called investment scenario, the annualized system cost is going to be like 8 million. Because this is in thousands of dollars. And compared to our reference, which remember for our case is just paying for utility costs and our existing boiler and electric heater or electric chiller, this is going to save us about 13% in costs. And emissions, it's also going to save us some emissions, probably because solar PV is renewable. And on the right-hand side here, you're going to see that this is what Xendee has optimized or calculated for our site to be the optimal investment as far as solar PV. Because remember, for the site, I had wanted Xendee to tell me what's the optimal investment for solar PV. And here's a table that summarizes some financial metrics that are often important to investors, financiers, or your customers. And I'll let you look in detail to understand what those are. So if you scroll down to our results, you'll see that we have several tabs here. And this report is going to look very similar to a report from a single node optimization. It's going to have most of the same things, except it's going to have a few extra tabs that aren't there for single node optimizations. I always encourage people to actually review all of their reports in detail so that you fully understand how your site's dispatch works, how it's getting its power, as well as where it's getting its savings from and what its biggest cost from. So as always, you're going to get a summary tab that summarizes your site's savings, its costs. And then the financial data tab is going to look very familiar to a regular optimization. You're going to get your microgrid cost breakdown. In this case, our microgrid cost is still going to be a lot of utility electricity purchases. And if you scroll down, you're always going to get our cash flow table, which is going to break down your costs by line items. So you'll see here we have our different costs for our utility, our CapEx for all of our different multi-node components, like our cables, transformers. And if you switch this to savings, you'll see this cash flow table, but from a savings perspective. So you'll see that most of our savings come from utility demand and energy reduction, and that's because we installed solar panels. So let's go next to our utility data tab, which this is just going to be a simulated utility bill of your new investment scenario. And then the next tab, energy balance and technology investments, is going to have nice visual charts that kind of summarizes your site's power balances, needs, emissions, different DER outputs and their balances. And at the bottom here, you are going to see that since we have losses from cables and transformers, it's going to be included in this chart here. But we can actually see the losses from our cables and transformers in a more detailed table, and I'll show you that in a little bit in our next tabs. But first, if you click on balance of systems, and this tab here is specific to multi-node, it is not going to show up in single node models. It's basically going to be a network bill of materials for your site. So it's going to count in all of our costs for our cables, transformers. Remember that we did enter costs for our cable and transformers before, so this is where they show up in reporting. If you don't enter any costs for your cables or transformers, then these are just going to be blank. And next, let's go to our dispatch by end use charts. So this is always one of the most important parts of your report because it actually shows you how your site is getting its energy demands over the different times of the week as far as, and also the different months. So for example here, this is going to be a snapshot of the load as well as where the electricity is coming from for a January weekday. If you click on the drop down, you can select it for different months. So for example, I can change this to a July weekend to see how the load is different as well as where the energy is coming from. And in multi-node, you're also going to get a new drop down. It's going to let you select a view for different nodes. So remember, in single node, you're just getting one aggregated view. But in multi-node, you can look at it from different nodes. So if I want to look at the electricity dispatch for, say, our node 1B, which remember is the actual building node for our building number 1, we can click on that. And that's going to tell us that at node 1B, all of our energy is imported from node 1A. And remember that at node 1B, we don't have any on-site generation, we don't have any solar panels, we don't have any generators. So all of the energy is imported. And remember, it's being imported from node 1A because that's a primary node at our building number 1. So let's switch over our node view to node 1A. And again, you're going to see that all of the energy is imported from the feeder because that's where it's getting energy from. And then if you switch over to the feeder, as we expected, all of its energy, or most of its energy, is coming from the utility connection. But you'll see that some of its energy is actually imported from node 2A. And that's probably because we have excess electrical production from our solar at node 2. So then we can kind of work our way over there, see what's going on. So if you click on node 2A, you're going to see we're going to have a lot of energy imported from node 2B during the daytime hours and imported from the feeder during the non-daylight hours when there's no solar. So then if we go all the way to node 2B, which remember is our actual building for node 2, this is where our solar generation is going to show up because the solar is connected at this load. So you'll see we have our solar generation here, but in the non-daylight hours, we still need to import electricity. So these different views are helpful to help really understand exactly where your energy is going to and coming out of, because remember, these cables are bidirectional. And so this is our electricity dispatch. And remember that we do have a heating load on node 2 and a cooling demand on node 1. So this is also where you can check those out. So that's the dispatch. And then let's move on to our power flow tab. The power flow tab is also only specific to multi-node models and only when you enable the power flow options in your optimized window. Remember, in your optimized window, we had to enable consider power flow. If you have it disabled, then you're not going to get this power flow tab. So the power flow tab is going to give us some information about both our network voltages and our losses. So remember that we had set those voltage minimum, maximum. It was like 0.95 to 1.05, very standard. So in this case, this chart just tells us that we don't have, any crazy voltage drops. And the network losses chart is going to actually break down our electrical losses for our different cables and transformers. So for example, it looks like in this case, our biggest loss is going from node 1A to 1B, which remember is being connected by a transformer. And if you change the power flow specifications in your cables or transformers, that is going to affect the losses calculations, which will reflect here. And then if you scroll down, we're going to see some charts for our voltage, active power, and reactive power. And kind of similar to the dispatch charts, you can also change the view by months, the day types, as well as the nodes that you want to see this from. So let's take a look at, for example, the utility connection node. So you'll see that the voltage consistent here. We are going to have a lot of active power because the utility connection is sending power to our site. And we are also going to have reactive power because remember, in this case, our utility connection is our slack bus. So it's stabilizing the voltage for our site. If you change this to, say, let's go to feeder 2B. So remember, feeder 2B is where our solar panels are. So again, consistent voltage. And you'll see that the active power, it now reflects kind of what our solar generation looks like. But it's not going to have any reactive power because solar doesn't have any reactive power in this case. It's not incurring anything. If we go to our node 1B, which is our other building, we're going to see that there's no active power because remember, there's no actual electric generation going on at that node. So feel free to explore this more on your own. And then lastly, we are going to have our operation summary tab, which just summarizes like how much your on-site DERs were working over the year or how much they were utilized. And lastly, we have our print report tab, which allows you to customize as well as download a PDF report of this optimization. So you can customize your reports and enable or omit things or charts that you want in your report. And if you click preview report, you're going to get a nice printable version of your optimization with financing metrics, investment indicators, savings and emissions percentages, as well as kind of all the charts, because I didn't disable anything in this case. So I'll let you explore this on your own. So just to wrap up reporting, I highly encourage you to actually dive into every single report and tab on your own when you get the chance, because I know I went over this kind of quickly, but it's important for you to actually understand exactly how your microgrid works and where all the costs and savings are coming from. And when you have an optimization result, remember that we can directly convert any of our projects directly into a one-line diagram. And that's where you would do here. You can open this project as a one-line. And what this is going to do, it's going to create a one-line project based on the results of this optimization, as well as all of your model components in your project. It's going to save your multi-node project as is. It's just going to create a separate one-line project. So if you do that, it's going to ask you, like some formatting questions and unit questions. And you can create a one-line diagram for there. For the purpose of this demo, we're not going to do that, but feel free to explore the one-line tool on your own. And we also have documentation as well as guided tutorials on just how to do the basics in one line. I'm going to cancel out of this. So that's all I have as far as a multi-node demo today. Remember, you have 1 week for this trial access of your Xendee account. So I highly encourage you all to play more with this model, or if you want to learn more just about the basics of multi-node, or not multi-node, microgrid modeling, check out one of our guided tutorials, and that's going to be more helpful if you want to learn about the fundamentals of microgrid modeling and actually learn how to set up from the very beginning to the very end. Because remember, this project, we kind of jumped in straight into the middle, but there's a whole lot that goes into actually setting the table or a multi-node project. So remember, we didn't touch any of the electricity tariffs, fuels, financing methods, or even outages. So be sure to check out guided tutorials on those if you want to learn more about microgrid modeling and get the most out of your 1 week trial license. So I will send it back to you, Lulu.
Thank you, Rita. So that is all for today. Thank you so much for joining. We will be sharing a recording of Rita's section tomorrow so that you can work on your modeling with her guidance. And the full recording will also be available next week under Xendee University on our website. We have more sessions coming up. The next one will be focusing on financial methods. So again, thank you so much for your interest in Xendee and multi-node, and we hope to see you next time.